All right. Yeah. Hi. Thanks for the invitation. Like everyone else has been saying, it's great to be here. Um, yeah. So yeah, I'm going to talk about quantum complexity of Hawking radiation. But I thought before I do that, I'd give a little status report on firewalls. So yeah. So these troublemakers think that you burn up at the black hole horizon. Clearly, we should understand this. Um, so far, the argument has it's held up fairly well. I think no one has really been able to convincingly dispense with it. Um, and that's not because people aren't trying. Um, so yeah, like Joe just said, I think at this point it's very clear that there's something deep that we don't understand about black holes and the information problem. Um, so yeah, when I said convincingly refute, yeah, so I mean, I don't just mean complaining about the details. I mean, even though I love doing this and I do it to them all the time, um, I think if we're really going to kill this, then we need a model where in the model, all the moving parts are really there, and you can see that there's a smooth interior and that the information gets out. And people love writing papers where sort of one of the things is clear in the paper, and then they say that there's no problem. But I mean, I think that's just not going to be enough to convince everyone. Um, so yeah, like Andy just said, conversely, if you think there are firewalls, then clearly we need a model of how that happens. And I think the most important thing is why it doesn't happen in other places. Why we're not seeing firewalls all the time during inflation, in Minkowski space. I mean that neither of these things have appeared, and I'm not going to give you one. Um, but I will introduce a set of ideas which, yeah, I hope may be an important ingredient in really constructing a sort of firewall-free model. So yeah, I guess my Bayesian prior is still on there, not being firewalls. And this will be based on work with Patrick Hayden, which I guess by the standards of this field is ancient by now since it came out in January. Okay, so my basic strategy is to think about, can you really, can people who are living in the bulk really test the contradiction that's at the heart of the AMPS argument? And here I'm going to use the old AMPS argument. Um, and you could say, well, who cares? I mean, if there's a contradiction, there's a contradiction. But I would say not necessarily. So to choose a favorable historical example, think about the uncertainty principle. So Heisenberg said, okay, there's various restrictions. You can't measure both the position and the momentum of a particle. And Newton might have said, who cares? I know it has a position and a momentum, and I don't care that you can't actually measure them because of some grubby problem with your detector. But yeah, I mean, obviously the classical physicist was wrong, and the operational restrictions, I think you could interpret as really telling you that the particle is behaving in some way that would have been contradictory if those assumptions had been really correct, but they weren't. Okay, so that's sort of the philosophy behind Patrick and I's work. So okay, just to be fair, I think a less successful example of that kind of philosophy is S-matrix theory. Fields aren't observable, should only look at measurable things. I mean, clearly that was not the best idea. Missed things like RG, instantons, you really need the fields. Yeah, I mean, some stuff came out of it anyway. Okay, so another, coming back to black holes, another example was the old story about cloning and unitarity and black hole evaporation. Okay, so here's some picture. Let's see, do I have a pointer? Yeah, okay, great. Yeah, okay, so the idea is, you make a black hole out of some infalling shell. Here's the nice slice that Joe was talking about. And then the idea is that, if we think that the evaporation is unitary, then it looks like you've got a cloning machine because, you can throw something in here, and then you've got a copy of it up here, but then you've also got a copy of it out here in the Hawking radiation. And it has to be able to do this to superpositions because you can throw in sort of superpositions, and that violates the no cloning theorem. But then the argument that people in the 90s gave against this is that well, no one gets to see the cloning in some sense. You can, if you stay up here and look at the Hawking radiation, then by the time you jump into the black hole, you can't see the infalling shell. It's so tightly pushed up against the horizon here that it's buried in the UV degrees of freedom. And on this slice, it's way over here, and causality prevents you from being able to see this. And then alternatively, if you jump in, if you ride the shell in, then you get to see the information there, but then you're not even close to being able to see the Hawking radiation out here. So here really the operational restriction comes from causality. Okay, so indeed complementarity, was the idea that maybe the shell here and the Hawking radiation here aren't really distinct degrees of freedom in the same Hilbert space, and that's okay because no one can see both, and it's just like position and momentum. Okay, which of course is why I think Lenny called it complementarity in the first place. Okay, so the AMPS argument now is a reformulation of the information loss problem, where indeed all the arguments all the parts are sort of accessible to one observer. So you can't hide behind complementarity any longer. You've really got to confront the problem directly. Okay, so I'll sort of briefly review the argument since the previous speaker was lazy and didn't review it. Here's some observer who jumps into the black hole. So this is the observer whose sort of causal diamond you make the argument in. So A here, so I'm afraid I'm using, I guess, the Northern California notation instead of the Southern California notation. So A are some right-moving Rindler modes in here, which Joe is calling B tilde. Then B are some right-moving modes outside the horizon, which Joe is calling little b. And then R is the early Hawking radiation. And then the goal is to describe the quantum state on this red slice, to just come up with some quantum state on that red slice. And you want it to be consistent with both unitarity and the horizon being smooth. Okay, so from Rindler space, you know that a smooth vacuum requires A and B to be entangled. So this is some picture that's supposed to show you that, and I'll write it like the entanglement like that. And okay, there's this calculation. You can show that the Minkowski vacuum looks like this, and then you can just evolve this mode up here and this mode up there, and they become these modes here. But the paradox arises because once the black hole is old, in the sense of having radiated away more than half of its entropy, then unitarity plus scrambling, and I think that's actually the plus scrambling is important, also require B to be entangled with the radiation. Or more carefully, I guess B has to be entangled with some subfactor of the radiation, which is usually called R sub B, whose Hilbert space dimensionality is equal to that of B. Okay. Yeah, RB, you can think it's often called the purification of B. So and then, so here's the crux of the matter. This is a problem from the point of view of strong subadditivity because, well, if this is 0, and then you can show that that means that this is just equal to SA, and then that tells you that, well, the mutual information is 0. Well, sorry, so the mutual information is greater than or less or equal to 0. Then this says it's less than or equal to 0, so it has to be 0. But if the mutual information is 0, that's completely inconsistent with any kind of entanglement between A and B. Okay, so that's the firewall argument. If you haven't heard it before, you have now. Okay, and now you might object that Alice, falls into the black hole and hits the singularity. So does she need to see unitarity? Well, so okay, here's where we have to introduce Charlie. So Charlie is somebody who stays outside. And Charlie can also look at B and R. So you see I've carefully chosen Charlie's spatial slice to align with Alice's spatial slice in such a way that B and R are sort of, you're really looking at the same degrees of freedom. And then since, they're obviously accessible to both Alice and Charlie, we should have the reduced density matrix on the two be equal. So this an important assumption. I mean, it seems if you didn't have this, then you'd get into all sorts of weird contradictions. Okay, so that's the end of the review. And so now let me sort of try and get into the way that Patrick and I have been thinking about this. So indeed, what we'll argue is that, well, not so fast. Actually, so for Alice to actually be able to verify the entanglement, she really needs to be able to access R sub B, which is this subfactor of the Hawking radiation that's supposed to be entangled with B. And in order to really see a violation of strong subadditivity, or to see a violation of the monogamy of entanglement, she's got to then be able to jump in and look at A, and then she'll see, get, if she sees a smooth horizon and she sees B and RB being entangled, then she'll get confused about quantum mechanics. But we'll argue that actually she can't access R sub B because of computational restrictions. She just fundamentally cannot access R sub B and still have time to jump in. So indeed, if that's true, then maybe there's a new kind of complementarity where Charlie sees that B is entangled with R sub B. S is needed by unitarity and scrambling. But of course, Charlie can't see A because remember A is behind the horizon. And then Alice sees B entangled with A, but she can't access R sub B since it's too computationally difficult. So okay, that's some set of words, and sort of by the standards of the field in the 90s, this might have been considered a convincing argument. But I think like I said in the beginning, by now sort of we've learned that you really need a model, and that the fact that there wasn't a model in the 90s, I think, caused people to miss the AMPS argument. So yeah, anyway, right, I interpret this as suggesting that maybe their assumption about the structure of the Hilbert space is too restrictive. It's like thinking that the particle has both a position and a momentum. Okay, so yeah, now I'm going to try and get into the details of making this argument. So I need to be considerably more precise about what Alice is actually trying to do when she verifies the entanglement. And actually it's notationally annoying, but it's more convenient to actually describe in Charlie's description, Charlie being the person who stays outside, since I would say Charlie's description is sort of less controversial. And since, currently I'm assuming the overlap rule, then that's allowed. Okay, so now I start writing equations. So Charlie's unitary theory, we can think of the state of the system, being in a pure state in some Hilbert space, where to interpret it semi-classically, we imagine that the Hilbert space factorizes into a product of three things. So here H is the stretched horizon degrees of freedom, the degrees of freedom that are sort of quantum gravity degrees of freedom in the black hole. B are the quantum field theory degrees of freedom inside the angular momentum barrier at 3 GM, so often that's called the zone, I guess, these days. And then R is the radiation field outside of the barrier. And from now on, I'm going to think of everything as qubits. And so I have to give names to the number of qubits in all of these, which the names have quantum information theory origins, but for now, just accept them. So R has n qubits, H has m, and B has k. And so you can think of all of those as being of order, those numbers as being of order the entropy of the black hole. Okay, so that's the model. Although, for the black hole to be old, we need this restriction. Okay. Okay, so here's the most important equation in the talk. This is the equation you should remember. It says that the state psi for the old black hole is in a situation where the zone, the atmosphere here in B, and the stretched horizon in H are indeed maximally entangled with subfactors of the radiation, where, to make this notation a little more explicit, right, I'm just, these are the k qubits in B and H, and then so this is some subspace of R where the last n minus k minus m qubits, oh, sorry, that should be an m there, not a k, are 0. And I emphasize that, so I've chosen the basis for B and R to be a basis which makes sense from the point of view of local physics, local measurements in the bulk. So what that means is I have to include this UR here, which is a complicated unitary transformation, which relates the basis of the radiation, where it's simple from the point of view of a photon here, photon there, to the basis where the entanglement is manifest. So indeed, if this U was not here, then this would be sort of manifestly a maximally entangled state. Okay, so that's what I just said, and indeed, yeah. So the basis where the entanglement is clear is often called the Schmidt basis. It's good. So UR is the star of the show. UR will be what I'm going to discuss for the rest of the talk. So make your peace with it. Because indeed, to verify the entanglement, all Alice has to do is act on the radiation with UR dagger. If she can do that, she can now, now she's back to the original state, and just by doing local measurement, she can test her favorite Bell inequality or do whatever else it is she wants to do to confirm entanglement. And this task of, acting with a unitary is called doing a quantum computation. That's what quantum computation is. It's doing a unitary, you're doing your favorite unitary. and the study of how hard it is to do, which is, so I'm going to claim that it's hard to do this, and so that's called quantum complexity theory. And the basic question, you ask how does the problem scale with n, where remember n is the number of bits in the radiation. So let's just get oriented with the numbers here. So for a Schwarzschild black hole, the evaporation time scales like n to the 3/2 because, well, the entropy is m squared and the evaporation time is m cubed. So from a complexity theory point of view, Alice has got to be fast. That's a low order polynomial. So for comparison, multiplying two n by n matrices is n cubed. Although I guess there's big money in decreasing the 3, and currently it's 2.3. But by contrast, in quantum mechanics, right? I mean, so if we just solve this on a classical computer, we'd be multiplying 2 to the n by 2 to the n matrices, okay? Because n qubits have a 2 to the n dimensional Hilbert space. So this is really fast. It's basically saying that Alice's task can't be harder than just multiplying some matrices. I mean, and not in the sort of trivial sense in which all of quantum mechanics is multiplying matrices. So indeed, Patrick and I argued that verifying the entanglement between B and RB typically takes a time which is exponential in the entropy, okay? And of course, this is ridiculously bigger than that, so then you're not even close to being able to have time to verify, for Alice to be able to both verify the BRB entanglement and test the AB entanglement, okay? So in order to argue for that exponential, I need some model of a quantum computer to assess how hard it is, to really, see, to do that. So there's a standard model, like for most fields these days. And the idea is that, you want to make some element of u 2 to the n acting on all the qubits. So you make it up by acting with elements of u4, which are called gates, just on the qubits 2 at a time, and then just acting in succession. So here's 4 qubits with some gates. And then it's, so you can show that you can make everything this way, okay? And actually, you only need one kind of gate, actually. So if it's sufficiently generic, and you can make everything, to arbitrary accuracy. Good, so then a finite sequence of gates. So you might have just said it's a unitary transformation, but in this language, it's called a quantum circuit. And then the number of the gates for the circuit is called its size. And then the size is what I'm going to take as a measure of how hard it is to do the computation. So that, that makes sense. Certainly if you have to do the gates in succession, then the time is just proportional to the size of the circuit. Good, so how many gates are needed to approximate a generic unitary to accuracy epsilon? Well, so here's the answer. I'll tell you the answer first. It's 2 to the 2n times log of 1 over epsilon. So the log, we can forget about it. But I just put it in because it's obvious it should diverge as epsilon goes to 0, and that's how it diverges, so it's pretty weak. You can get pretty accurate without paying much of a penalty in the log. And it's very exponential. It's fast, slow. It takes a long time. So okay, to derive that is pretty easy. You just, so the number of circuits of size t, well, there's an n choose 2 here because you've got to pick, for each gate, you've got to pick 2 qubits to act on. The order matters, so there's a 2, and then, these are the number of gates, so that's how many gates there are. Whereas the number of balls of radius epsilon you need to cover u 2 to the n is of order 1 over epsilon to the 2 to the 2n. So then if you equate these, that gives you a sense of, how big your circuit needs to be to make a generic unitary transformation. And of course, okay, you take the log and you get this. All right. So indeed, exponential. Okay, so yeah, doing more than one gate at a time doesn't help, since you'd have to do exponentially many at once to try and beat this down. And then, then it's still exponential time. You've just got to communicate from one part of your computer to the other. Other trivial variations don't help. It's worth mentioning, this counting is the fundamental reason why quantum computers aren't that great. They're helpful for some things, but they don't solve everything, and that's why. You still need exponentially many gates to do your favorite thing. All right. So of course, now that's for sufficiently generic unitaries. You might ask, is UR really sufficiently generic that counting should apply? It seems obvious that maybe it shouldn't be. The black hole doesn't take exponential time to make this state, so why should it take us exponential time to unmake it, so to speak? can we do some time reversal? Okay, and the answer is no. So we need to understand a little better how the black hole works to see that. So here's a model. What the black hole does is it's got some time evolution operator here, which I'll call U dynamical, which is, think of it as the time evolution operator of n equals 4 super Yang Mills. So it takes some initial state where the number of initial states here is, the entropy of the black hole, and then it evolves it into some state like what I was talking about before, where now all the information about the microstate is contained in this matrix UR here. So then U dynamical, for various reasons which I don't have time to get into, we should expect that U dynamical has a polynomial sized circuit, which means that we can act efficiently with U dynamical. So it seems like you should just be able to use U dynamical dagger, and indeed you can make a simple circuit UR tilde dagger with the property that it acts on psi as UR dagger, all in polynomial time. So that sounds good. But of course, the problem is you used U dynamical to make this, and U dynamical's gates act also on B and H, and not just on R. So that's cheating, right? Alice is supposed to work just on the radiation. We certainly are trying not to grant her the ability to directly manipulate the black hole degrees of freedom. So she only has access to part of the system, and so this UR tilde is useless for her. In other words, inverting a unitary is much harder when you don't have access to the whole system. Okay. So in fact, so each I needs its own URI, whereas there's only one U dynamical. There's only one time evolution operator. And what that means is you can make a counting argument, which I don't have time to get into, that really, almost all initial states necessarily require exponential time to decode. Only a vanishingly small fraction of them have even a chance of having a UR of I, which can be simulated in polynomial size, and that's a rigorous proof. So, okay, you could still wonder if there's some basis of initial states where the decoding is easy, sort of along the lines of what Joe was saying earlier today. I won't have time to discuss that here, but it seems pretty unlikely. Okay. You can also try and make some crazy computer out of black holes. That doesn't help either. Okay. So finally, okay, for Schwarzschild, this seems pretty clear that, it's not even close. We can try other things. So charge, angular momentum, putting in ADS, all these things don't seem to help. The most dangerous candidate, which I guess was suggested to us by Juan a while ago, is to take a big ADS black hole and then put it exponentially far down a long but finite throat. So I have to write this equation in some talk. That asymptotes to 10D Minkowski space. And then, the black hole will decay very slowly, even though it's a big black hole, because energy can leak out into the 10D Minkowski region. And then you can also imagine outsourcing the computation, not to Pakistan, but instead to up the throat to the 10D region. Okay, so this introduces new problems, however, in that the barrier makes it, essentially the whole point that Juan taught us is that, well, Juan and also Igor, that the region down the throat decouples from the region out in the Minkowski space. It's very hard to send signals back and forth, and so far it seems that the timescales work out in such a way that Alice can't really verify the entanglement. You can ask Joe later if he agrees with that statement. So yeah, Joe and his friends have tried to avoid this by replacing the asymptotically Minkowski region with some arbitrary system with no space-time interpretation. Okay, so that's pretty confusing. There's sort of weird interpretational questions that you get into, and I think, although I won't have time to really get into it here, that some of what they say is inconsistent with how I understand the eternal two-sided ADS black hole. That's okay, because I guess Juan's probably going to talk about that, although we'll see. So I think for now, it's probably better to focus on thought experiments done strictly by observers living in the bulk with, well-defined low-energy initial conditions. Otherwise, I think we can't really be too sure what to expect. Maybe crazy things do happen. Okay, so in the end, there's much more to understand. I completely agree with what Joe said. So, as I said in the beginning, I haven't managed yet to implement these ideas into a real model that I'm satisfied with. So, I think this is a loophole to the argument, but I don't know whether or not there's a model that can take advantage of the loophole without running into some other kind of trouble. Okay, so thanks for listening. Kamsahamnida. And I'll leave you with a picture that I found online last night of black hole formation and evaporation.
Thank you very much. Questions, comments? Andy?
Usually in quantum mechanics, we assume that the quantum state is exactly measurable. In other words, we allow ourselves to repeat the experiment e to the entropy of the black hole times.
Yeah.
And we can, so that we can measure it exactly. We don't care if it, how much it takes. Now, are you saying, is what you're saying quantum mechanics? Are you violating?
Yeah, no. So I want to maintain that. So I think the thing I would challenge here is the structure of the Hilbert space. I would just, there's some assumption in all these arguments. Remember I said like, well, I don't want to go all the way back, but that, you can imagine the real microscopic Hilbert space is factorizing into modes here and modes there. And the motivation for that, I think, is that, well, you could imagine someone flying around looking at those modes, so they somehow have to exist in the theory. So I think what I would be saying is just that, hold off on that, and maybe the structure of the Hilbert space and its low energy interpretation is more complicated than we thought. But I still definitely want to be doing quantum mechanics. It's just I just want to say maybe the structure of the states is not quite what these guys say it is.
I have a variant of this question, which I think I also asked you before. When we studied quantum mechanics, this question of how long it takes to extract the information was not discussed. Is it because the books were incomplete, or is it because quantum mechanics is incomplete?
Gee, well, I mean, I don't think I'm really challenging the foundations of quantum mechanics as written by Dirac in his book. I think that, but I think that this is a useful set of tools, and I think. Well, I mean, like Joe said, if we really had a theory of quantum gravity, we probably wouldn't have to have this discussion because we could just look and see what what the theory does. So the problem here is that we don't know the theory, so we're sort of trying to decide what are reasonable criteria that we want the theory to satisfy. And in that regard, I think, so yeah, there's been a point of view which Scott Aaronson has been pushing for a while, which is that, when we make theories, there are things like superluminal propagation that we don't like. When someone writes down a theory and it has superluminal propagation, we're suspicious. Well, yeah, I guess what Scott has been arguing is that, well, yeah, so we should also have some sort of restriction, which is that, changing the laws of physics, when you write down a new theory, it shouldn't allow you to do ridiculous things. So a simple example is that if you make quantum mechanics a little bit nonlinear, then you can now solve NP-complete problems in polynomial time and automate theoretical physics and cost us all our jobs. And it seems like that's kind of crazy. So yeah, I don't know. I feel like it's an interesting set of ideas to take into account in sort of when playing with possible theories. But yeah, in the end, I mean, I think in the end we'll have some theory and we'll see what it does. And I hope it'll still be quantum mechanics. Well, actually, it would be interesting if it's not, but hard to see how that would be.
Okay, we have time for one more question. So the microphone is coming.
You said that the computational complexity of deciding entanglement is order 2 to the n.
Yeah.
But it is an open problem in quantum information community. It's an open problem.
Well, let's be careful. I mean,
Yeah.
so what I said was that to implement a generic unitary transformation requires exponentially many gates. That's a theorem. There's no controversy about that. What's less clear is that once you start including the restrictions on UR that come from the black holes, whether or not the transformation that you get will be sufficiently generic, that it will require exponentially many gates. So again, I gave a proof that for a generic initial state it will require that, but you can still ask whether sort of for special states should it be true, and then indeed you run into unsolved problems in quantum information. For example, about the computational complexity of doing quantum error correction. So yeah, there was no way I was going to be able to get into that in this talk, but you encounter things like QSZK complete problems and this kind of thing. And there's still definitely work to be done.
Okay, well, let's thank our speaker again.